Hey guys, BuildZoid here, and this is going to be a purely theoretical and therefore extremely dangerous video about potentially how you can. Actually, no. There's one part which I'm 100% certain about, and there's another part where I'm like 95% certain it'll work, but without a card in hand, I can't actually verify it. So anyway, how to modify the UP9512. If anybody's wondering why we're talking about the UP9512, well, the UP9512, well, I finally got like a pinout for it. Not a datasheet, just a pinout. And that pinout has a lot of pixels, as you can clearly see. See all those pixels? Yeah, unfortunately they didn't, like, seriously, this is the highest resolution image of the UP9512 pinout that I've found. And the good news is it's basically a UP9511 with a bunch of bolt-on upgrades, which is why I'm doing this video, because it functions. I'm almost certain that it functions very, very similarly. We can therefore do quite a lot of things that we did on the UP9511, except for, say, VRM switching frequency, because unfortunately, VRM switching frequency is on a pin that's getting multi-purposed for I2C addressing. So pin 26 right here has, I mean, you can't read it but it basically what it says right there is ADDR and /FSW. And the great thing is, like, this is what we want. That's our switching frequency of the VRM. And basically cranking that up can improve our VRM output ripple. But unfortunately, it is multi-purposed with the I2C addressing. And that basically means that I have no idea, like, really bad, like, you're not going to be, like, unless you have the data sheet so that you can change the frequency and keep the same address as whatever the resistor that's currently there does, you're probably going to have a really bad day. Also, I'm pretty sure that the switching frequency setting is, like, it's not, it's not granular. Like, you can't just go from like a 3, like, it's not like you can just take a potentiometer and turn it and it'll linearly increase and decrease your switching frequency setting. It's almost certainly going to be very specific resistor values for a specific combination of address and frequency. And so without a datasheet, we unfortunately really can't do anything about that part of the controller. But what we can mess with is the load line. With a 95, like, that's the part I'm 95% certain about. And we can of course get full manual voltage control, because see these 4 pins right here. I mean, ultimately we only really care about these 3, but this is the standard NVIDIA PWM vid interface. This thing is super easy to modify, because essentially the way this works is PWM signal goes into pin 39. It comes out of pin, then it does some stuff in the chip, but more importantly, it comes out of pin 40 here. Then it goes into a bunch of circuitry that eventually that connects it to VREF and ref in, and ultimately it gets converted into a voltage that gets fed into the ref in pin, and whatever you feed into ref in is what you get on the output of the VRM after load line adjustment. So yeah, which is just something you need to keep in mind. But basically what you do if you want to get manual voltage control is you disconnect your ref ADJ from, well, everything, because it's only really connected to these guys. And then you can set up a potentiometer between ref in and vref. So if we actually look at the card here, so this is a EVGA FTW3. So if anybody's wondering about when I'll be doing that, when I'll be doing a PCB breakdown for it, soon. Probably right after I do this video, actually. But basically, if we look at the pinout here and compare it to our chip on the board, well, we can orient ourselves because there's a dot right here, and that dot corresponds to this dot right here, so that tells us that this guy is ref ADJ. That's ref A. I'm just going to leave it as ref A because it doesn't really need more than that. Then we have ref in, so that's our voltage setting, so whatever you put on that pin is whatever you're going to try to get out. And then we have VREF, and VREF is basically just straight 2 volts, so that's just 2 volts output. There's a capacitor on it to filter it a bit, but ultimately that's just straight 2 volts. And basically what's going on, there's a connection between ref ADJ and there's a bunch of resistors and stuff. Like, we don't care about the stuff because we're disconnecting all of the stuff. That's why I'm referring to it so broadly. We don't need to care about it because we're going to disconnect all of it. But essentially what you'd do is you would take a digital multimeter and you would trace between ref A and ref in. And I'm almost like, I'm going to say 90% certain that it's going to be this, or this resistor. And basically well, it could also be this one, I guess. There's a bit too many resistors in this area because, yeah, it's a multi-layer board, and you can see that there's a bunch of vias in the area, so it actually makes it like, well, that via is obviously pin 3 there, but like this, I think that's something coming up, actually. But anyway, ultimately, just multi-layer board, really hard to actually tell anything from just a picture, but we can trace this out. Like, that's what I've done for the 1080 Ti's, because I don't have schematics. They're not public. But anyway, and I've not found any place where you can occasionally find schematics. But ultimately what you do is you would trace from ref A, and ref A seems to probably go to this guy, this guy, this guy, this guy. No, I don't think it goes to that one. Actually, maybe it does. So possibly that one as well. But I don't think we'll have to mess with that one. And then what you're going to want to do is you're going to want to trace from ref in and check a bunch of resistors. And ref in probably goes to this one. So let's put an extra little X there, and maybe this one. Possibly this one, and possibly that one. So yeah, you know, the multi-layer board, it's going to be a mess. But ultimately, what you're going to want to do is you're going to want to disconnect the resistor connecting ref A to ref in. And that resistor is probably going to be like 21K or something around that. Just if I'm remembering the values for a 1080 Ti properly and a 1070. And they're like, that circuit barely ever, like, I don't think that circuit ultimately ever changes. But yeah, it's going to be like somewhere around 20K, might be 18K or something like that. So there's going to be a 20K ohm resistor. And once you remove that, what you're going to have is a open loop between ref A and ref in. Like, if you try to measure the resistance between them, it's going to be like mega ohms or something huge like that. Or it's just going to straight up tell you that it's like open loop. And at that point, you've achieved what you wanted to do. You've disconnected the software voltage control from the actual voltage control, right? Because kind of messy terminology, but like whatever voltage we have on ref in is the voltage the VRM is ultimately trying to output before load line adjustment. So we want to disconnect ref A because ref A is the software control. So once we disconnect ref A, we've disabled software voltage control. So once we disconnect ref A from ref in, we disable the software voltage control. And at this point, what we're going to want to do is we're going to want to hook up a voltage divider to ref in with some limiting resistors so that we can control our voltage. And ultimately, the voltage range we generally like on 1080 Ti's, what I normally set up is something like 0.6 volts to 1.7 volts. Now, on Turing, I don't think it's going to scale all the way to 1.7 volts, and ultimately you want to limit your maximum voltage so that you don't break the card, because if you shove like 2 volts into a Pascal card, I'm pretty sure it's going to be dead, regardless of if it's on liquid nitrogen or not. But anyway, so for a Turing, I would probably limit it to 1.5 volts, but, you know, it might be fine to leave it at 1.7 volts. Ultimately, I don't know the process that well. I don't have a card to test, but you do like this is a good range, and that 0.6 volts is just like the minimum voltage which these cards will run on. So that's why I generally set it to 0.6 volts. So how would you actually set that up? Well, the way I normally wire it is that it looks like, and we're just going to pull this off to somewhere here. I don't like that. It was too clean. So yeah, anyway, so we have our 2-volt wire right here, right? That's still at plus 2 volts. And then we're just going to set up a little potentiometer. And yay, there's our potentiometer. Then we're going to put our limiting resistor. So this one limits our maximum voltage. And we're just going to hook that up to straight 2 volts. So that's what that is. And then we're going to put our minimum voltage limit. And actually, like, they ultimately affect each other all. So if you if you set this one upwards, it actually raises your maximum voltage up a bit as well. But you're like, this one is the one that like has most of the control over your maximum voltage. Anyway, at least depending on how you wire it. But actually, I shouldn't have said that at all. But whatever. It's just like that's the way I think about it when I'm setting up my circuit. So And the values I like to use is 1K on the middle one here. This is normally I have it as a 680, and then this one is either a 330 or a 390. And the reason why I have it set up like this is because it all adds up together to like 2000, roughly 2000 ohms total, right? And this is 2 volts, and basically it means that if we push this all the way to push the potentiometer all the way to ground, right? Because this goes off to ground, of course. If we set it all the way over there, we get about 0.65 or something like that, 0.68 volts or something like that. And if you set it all the way to there, you get 1.7-ish or like 1.68, depending on what specific value you use. So yeah, that's how I like to set that up. And you can actually calculate the specific values, but ultimately it's just like there's not like when you're setting up your safety limits, it's just like you want to put your safety limit so far away from like instantaneous danger that, plus minus 50 millivolts or whatever doesn't matter, which is why I'm not giving you specific values. It's just like something around 1.7, something around 0.6. And by something around 0.6, I mean more like something between 0.6 and 0.75, because ultimately we're not going to be using that low voltage range anyway. Yeah, so that's how I like to set up the limits. And there, that gives you voltage control. Disconnect ref A from ref in, and then set up a little voltage divider with some resistors to limit yourself. If you don't use the limit resistors, the main reason I put them there is if you set the potentiometer all the way to plus 2 volts, well, your VRM is going to output 2 volts. And I'm not sure that the capacitors on the output of the VRM are rated above 2 volts, so it might break those. And it's also going to break the GPU core. So, and if you think it's going to be like there's going to be some warning, there's not. It's basically going to be, you set 2 volts, the screen's going to go black, and the card's dead. From then on, it's not going to put out any more image. There's no way to repair it. You've killed the GPU, like you've killed the silicon. So unless they invent some kind of nano machines that can repair, freaking transistors on a nanometer scale, you're not getting that card to work anymore, which is why, I put the resistors to limit the maximum voltages on every volt mod I do. Like, this is just something I always do to make sure that, you can't accidentally break stuff. So yeah, that's the voltage control taken care of. Now for the load line. Now, load line's a bit of a mess because if we look, this is pulled from the UP9512 datasheet. This is the load line equation. VSS right here is VSS is the output of the VREF in. So if we set our VREF in to say 1.2 volts, right, or whatever other voltage we want, we can set, but let's just say it's 1.2 volts. Then this is the actual output voltage of the VRM. So that's going to be VR out, right? So, and this is going to be the 1.2 volts right there. It's going to be 1.2 volts, and essentially what we're looking at here is that as your current increases, your droop increases, which is just how load line is supposed to work. But basically what we're focused on here is the current source is proportional to the output current, and RLL is an external resistor for adjusting the load line slope. RLL right here, and if we look at RLL, it goes between EAP and SS, which this is soft start. Now, how do you adjust this? Well, let's just think about it this way. Like, we're going to ignore the other values here. Essentially, what you can think about is if RLL is 0, then this entire block right here is 0, and you have no load line, right? There's no load line at all. You're going to have completely static output voltage, except for the fact that the VRM doesn't have perfect transient response, so there's going to be some regulation issues with that. But essentially, if you set RLL to 0, no load line. I mean, no V-droop. So if you set it to 0 ohms. So to do that, you would just short right over there. Now, for adjusting... now, what if you wanted to actually adjust your load line so that you have a little bit of droop or like a very specific... like just some kind of specific value of droop that you think works best? Well, if you want to do that, what you'd be doing is basically just reducing the value of RLL. Because if you... divide RLL by 2 or by 3 or whatever, like if you want 1/3 the stock load line, or you want 1/4 of the stock load line, right? You just have to divide RLL by like 4 or divide it by 5. Well, it ultimately that's gonna, because everything else here is being multiplied by RLL, right? Like this is all just being multiplied by RLL. If we cut RLL in half, the outcome of this block right here is going to be half as large, and that's going to reduce our V droop by half, right? Well, that's going to cut our V droop in half. So yeah, essentially for RLL, you're just going to be putting another resistance in parallel, or just going to short right across it, depending on what exactly it is you want to do. Ultimately, if you actually like fine tune it, there's probably going to be like a sweet spot where the load line is just perfect. Maxing it, like just completely soldering right over it, is probably going to be less than ideal for your actual stability under load, because Pascal, and I assume Turing is going to be the same, these things are extremely temperature sensitive, and having a load line actually really helps reduce your load temperature without actually reducing your stability, because ultimately, like, your voltage regulator is not going to be able to, like, the voltage regulator isn't capable of keeping up with a constant voltage output on a GPU core where the current draw changes up and down constantly. So you're still going to have, like, regular, like, basically what the load line allows you to do is, instead of having something that looks like, if we do a graph of like our voltage over time, instead of something that looks like, well, actually it would look more like this, where you have a giant dip and then it comes back up as it overshoots, and then it levels off eventually, right? Instead of having something like that, which ultimately you're still going to crash right there, right? That's the problem, is like you're going to crash right there. But on the off chance that you don't crash, and then you're going to have also smaller, smaller undershoots and that kind of thing. Like, on the off chance that you don't crash, this is a whole bunch of unnecessary heat, right? This is a whole bunch of extra power consumption that produces a whole bunch of heat. We don't really need that. So what setting up the load line properly would allow you to do is configure the V droop to, do something that looks more like this. And this is going to massively improve your operating temperature, and your minimum voltage is still the same, right? Because this is going to happen regardless of if you have the load line on or off. So that's why load line exists. Having the lower operating temperature will ultimately mean that you would basically be able to, say, run a overall higher voltage, right? So you could then set your core voltage to something like this, and at that point, your minimum voltage is now higher. You're still very well controlled. Your temperatures aren't any higher than before, right? Because this is below that old voltage level. So you're still running cooler. You have more voltage than before, because this dip is, still going to be there. So yeah, being able to fine tune your load line can massively help with stability, especially on something that's very temperature sensitive, like most of the modern manufacturing processes. So yeah, that's why you'd want the load line calibration controls, why you'd want to actually adjust it, not just short right over that resistor. Because if you do short right over it, yeah, you're going to get something that looks like a straight line, except for the parts that, where the voltage regulator can't keep up, and that's ultimately still going to give you crashes. Now then, the issue with doing that, though, on the UP9512 is that they've relabeled pin 28 from soft start to DAC, which is kind of annoying, except for the part where the UP9508 datasheet pretty much confirms what I was hoping for. EAP, right, which is the same. So EAP, non-inverting input of the error amplifier, which if we look at our load line configuration, this is resistor goes from EAP to soft start. This is from the UP9511 datasheet. Connect resistor between this pin and soft start pin to set the droop. So that's EAP again. EAP in the UP9508, which is a different datasheet, but I assume that the pin functionalities are going to be similar across most of UPI's product lineup. So EAP here is connect resistor between this pin and DAC to set the droop load line function. So I'd say it's pretty safe to assume that there's going to be a resistor between these two pins, right? Let's zoom out a bit. You're going to have something like this on those two pins where you have a resistor, and that's just going to be your RLL. Also, it's worth noting that the output voltage of this pin is the reference voltage for the Vcore rail. DAC voltage is measured, blah. Don't really care about that. Connect a capacitor from this pin to FBRTN, which is exactly, and a capacitor connected between SS and FBRTN sets the soft start ramp up time. I think it does the same thing on this one as well, but again, I've not actually read the data sheet that far. Ultimately, SS and DAC have a lot of similarities in how they're wired and how they work relative to EAP on the UP9508 and the 9511. Also, soft start is on pin 28, which just so happens to also be the DAC pin. So I'm just going off the assumption that, if we want to tweak the load line on the UP9512, you do it the same way. It's probably it's these two pins right here, where that one's DAC, and this one is EAP. And then if we look at how those if we look a little bit ahead, it looks like they probably go through that resistor right there. So this is almost certainly going to be RLL. And if we just put another resistor in parallel with that, we can tweak our load line down or up or whatever, right? So yeah, that's how we can configure the load line on this thing. At least I think you can configure the load line. I'm not 100% certain on that. But I'm like 95% certain that that's going to work, which is enough certainty. For me to actually try that if I had a card. I think I did the Vcore mods on Vega with the first one I did. That was I'm going to say that was 80% certainty. And I was just like, well, it's almost like this circuit looks really similar to what they normally use. So it's probably what I'm looking for. Did the mod. It is what I'm looking for. So yeah, I'm pretty sure here, this is pretty certain, almost certainly going to set your load line settings. So yeah, that's how you can configure the load line and the voltage control. Now, there's also this pin right here called PSI, which is the power savings interface, or power state interface. It's basically, this allows you to force the controller to run all the phases at the same time. Now, unfortunately, I've not actually bothered to look up how that's done on the 9511, but considering how similar this chip is to the 9511 in general, if you want to mess with the PSI, this is basically just a case of you need to pull this. You just need to pull this to a logic high or a logic low to force the controller to always be running all of the phases, which incidentally is terrible for your idle power consumption and your low load power consumption. And just generally, your VRM efficiency is going to be completely trash as soon as you're not running at 100% GPU load. But it can sometimes help with overclocking because it prevents... because it can improve the transient response just because you disable the phase shedding. And phase shedding actually, it's nice for efficiency, but it adds a little bit of delay when you try to turn a phase, take a phase from idling into enabled. That actually takes much longer than just turning a phase on and off as normal. So it can help to disable that and force the voltage controller into always running all of the phases regardless of loading situation. So yeah, that is it. And I managed to make this video longer on the reshoot. Anyway, so yeah, that is it. That is how to get voltage control and almost certainly get load line settings for a RTX 20 series GPU that uses the UP9512. It's also worth noting that the MP2888 seems to be mostly pin compatible with the UP9512. So yeah, if you had two, ideally I'd want to actually compare that on two cards that have those controllers, like a MP2888 versus a UP9512, and you could probably, based off of how this one works, you could probably figure out how the MP2888 works enough to get voltage control and that kind of stuff working. But yeah, basically, if you want to run Sub-Zero, you're ideal, you want voltage control on your GPUs, because once you're below, minus 20 degrees, Even something like Turing will probably will scale with core voltage, and then you can try tweak the load line up and down, and you can just try really tweak all of the things, or as many things as you can figure out how to control without, getting the full data sheet. Unfortunately, I really, really hope we eventually get that full data sheet, because then we could also mess with the switching frequency. But yeah, ultimately, if you are going sub-zero, then these are mods that could help a lot with getting better overclocks out of these cards. Just because, well, they'll actually scale with voltage once you take them sub-zero. And yeah, so at this point, I've actually detailed like every single mod necessary to completely control an RTX 20 series card. Disable power limit, I've already gone over that. Now you have voltage control, and it's just like, yeah, so at least for cards that use the 9512, because obviously there's the MP2888, and we don't have, like, I don't have a pinout for that one at all. So yeah, I'm not sure how you would deal with that one, but for the 9512 we have everything. So that is it for the video. Thank you for watching. Like, share, subscribe, well, everything, most of everything. Anyway, I'm gonna end it before this gets even longer. So yeah, thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. Also, thanks to Gamers Nexus for the UP9512 picture here. And what else did I want to say? Right, if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon and t-shirts. You can find both, a link to both down in the description below. And yeah, also, I should have put a disclaimer at the start of the video. Oh, well, too late for that. I'm going to go hit the stop button. Probably nobody's going to do anything I described anyway. I don't think, well, actually, no. I'm not sure that I'm not sure about that at this point. Probably nobody's going to do anything I described anyway. So, yeah, that's it. Goodbye. See.